Hey everybody, this is Professor Ross, and in this video we're going to talk about a theory-based approach to analyzing paired samples. We have been talking about this paired samples design throughout this unit, and we've looked at how we can analyze and do inference with a simulation-based approach. In this video, we'll be talking about a theory-based approach. Our key learning objective is to use the logic of statistical decision-making as we look at these inferential procedures. As usual, we have two different possibilities for approaching inference. We can do a simulation or we can do a theory-based approach. In the simulation, we simulated randomly swapping the order of calculating the differences in the responses, and we felt like that was a way to simulate the null hypothesis being true. But we needed computing power to do that. And nowadays, we have plenty of computing power to carry out those kinds of simulations. In the past, they didn't, and so they needed a theory-based approach because they didn't have the same kind of computing power. Um, so nowadays, it's always a good choice to think about using the simulation. However, we can use the theory-based approach when we meet certain validity conditions, and the theory-based approach can be especially good when we have very large samples because it takes even more computing power to do simulations with really large samples. So there still is a good place for the theory-based approach. Plus, many people haven't learned much about simulation-based approach and may only know the theory-based approach. So it's good to understand and be able to work with people who only know that as well. The theory-based approach does use the central limit theorem. And so it's the same theorem we've used all along. And so we're going to see a lot of similarities to other things we've said all along. We need to meet a validity condition in order to use the theory-based approach. So this is one of the drawbacks of the theory-based. We have to meet this condition. If we don't meet it, we shouldn't use this approach. Instead, we should use a simulation. We have an either or here. Either we can believe the population distribution of differences is symmetric. In other words, it's balanced on either side. How do we know what the population distribution of differences is? We probably won't know what it is, but we can get some insight usually from our sample. And so if we look at the sample differences and it seems reasonably symmetric, and we don't have reason to believe we have a bias issue in our sample, then we generally can feel good about that. The other possibility we can meet for a validity condition is a very familiar one for a quantitative response variable. You have to have at least 20 pairs and the distribution of differences is not strongly skewed. So once again, we're looking for at least 20 pairs and little skew in our sample, and that is a familiar condition for us. If we meet those conditions, we can do a theory-based approach. What does a theory-based approach involve? I'm going to show some of the things under the hood here. These are formulas that in the past have often been used by hand, but we'll use technology instead. But I do want to highlight how this really lines up with the things we've talked about before. So if our explanatory variable is a binary variable and our response is quantitative, and we have this paired design where the two responses are paired together in a meaningful way, then this is what we're going to be looking at. Our parameter is going to be the mean of the population differences. So the mean, and D stands for differences. So out there among the population, if we took all the pairs of data and calculated their differences, what would the mean turn out to be? That's what the parameter is. In our sample, our statistic is the mean of the sample differences. So it's X bar of the differences. And this is the interesting thing. We have two quantities that are paired together. But in our analysis, instead of paying attention to those two quantities separately, we calculate a new value, the difference, and we basically treat it as a single quantitative variable rather than thinking about it as two variables. Our theory-based approach formulas for the statistic, the mean of the difference in the pairs. The T statistic is our statistic minus the mean of the null distribution divided by the spread of the null distribution. And we can calculate that with the spread of the differences in our sample divided by the square root of the sample size. This is the same overall formula as always for a standardized statistic. Our statistic minus the mean of the null divided by the standard deviation of the null. So that works out the same way. Similarly, the confidence interval turns out to be the same overall structure. Our statistic plus or minus a multiplier times the spread of the null distribution. And so we have under the hood basically the same things going on with slight differences for how we calculate those different pieces. Once again, I don't expect you to use these formulas by hand. We can use technology instead. And we're actually going to use two applets to do this kind of work. We're going to explore our data in the matched pairs applet and get some of the statistics that we need to put into the theory-based inference applet. And we're going to go with the one mean scenario there. The single value, the single variable of differences is what we're going to be paying attention to. Let's try it out with an example. Does students' body fat change over the course of a semester? So we've got a set of data called body fat on the textbook website. This was data collected from a bunch of students at a college, and they checked their body fat at the beginning of the semester, and then they checked it again at the end of the semester. I'm going to go ahead and bring that data set up, and we can just take a look at it. Yeah, so here it is. And I already grabbed it from the textbook website and put it into the matched pairs applet. And so here we go. We can see there's a column of pre-body fat data and post-body fat data. These two numbers come from the same student. So they're paired in that we feel like that student, had the same experience over the semester, and the pre and post values are connected to each other because they come from the same student. So it wouldn't make sense to imagine pre-body fat as being one group and post-body fat being a totally independent group, because there is this close connection that each pair of numbers comes from an individual student. The graph here, all these lines are a little bit crazy because it's a pretty big graph, but we can see the distribution of pre-body fat here and post-body fat here in blue, but this is the distribution we end up wanting to pay attention to. It is the differences from each pair of data. So if I did 14.58 minus 14.17, I'd get a number. It would be a small positive number, and that shows up on the graph over in here, right? If I did 6.6 minus 8.98, I'd get a negative number, and that shows up on the graph over here. It's these differences that we end up analyzing and doing our inference with. And so the key values for us to understand from this applet here, why we even go here, is to understand what the mean of the differences is and what the standard deviation of the differences is. Now, we can ask ourselves, is it appropriate to do a theory-based approach, or should we stick with a simulation? We've looked at how to do that before. Here, we can either look at this distribution and say, does it seem like it's reasonably symmetric? And it does seem reasonably symmetric to us. So we could probably guess that the differences we'd see in the population would be a reasonably symmetric distribution. And that's a good sign. That means that we probably can do a theory-based approach. The other thing we could check is we could say, do we have at least 20 pairs? Yes, we've got 177 of them. And do we have no strong skew one direction or the other? Now we see a long tail here, but it's matched by this tail over here. So this data set does not look skewed in one direction or the other. And so we feel good about using a theory-based approach. How do we do that? How do we do a theory-based approach? If we do is choose randomize here, we're doing a simulation-based approach. To do a theory-based approach, we need the theory-based applet. And so if you go back to your applets, we were just looking at the data, exploring it in matched pairs. Now we're going to go to theory-based inference, and we're going to choose in our scenario, we're going to make sure we choose the one mean scenario. Now you might say, but we've got two things. We got the pre-data, the pre-body fat, the post-body fat, when we want two means. Well, we're actually not interested in those individually. We're interested in the differences we got between those. And so we really just have one variable we're interested in, the differences in body fat. How many of them pairs do we have? We had 177 pairs, and the mean of the differences was 1.15. So that's here on this graph, 1.155. And also that sample standard deviation of difference is 3.078. That was here, 3.078. We hit calculate with that, and then we can come over here, do our test of significance. The default hypothesis is that the difference is 0, mu is 0. And the default alternate is that it's not 0. Why? Well, the null hypothesis is that that the differences are going to turn out to be 0, because the null hypothesis would claim that uh, it doesn't matter which one we're looking at, pre-body fat or post-body fat. We shouldn't see any difference between those two. So that's what the null hypothesis always is, that the differences turn out to be have a mean of 0. And so that's the default one and the theory-based one here. So we're good to go there. We can hit calculate, and it'll bring us a p-value and a standardized statistic. The standardized statistic is just about 5. What's it saying? Our result, our difference of 1.155 is about 5 standard deviations away from that claim in the null hypothesis. Whew, that's a lot of standard deviations. That is not where a typical answer ends up, a typical result ends up. That's way out there. What's the probability of seeing a result this far out if this null is actually the truth? Our p-value says there's essentially no chance of seeing a result like this if the null hypothesis is true. So we have very, very strong evidence against the null hypothesis that the mean of differences is 0. We reject that. It looks like the mean of differences is higher than 0. We should ask ourselves what that's telling us, that we have a positive mean of differences. And what would that mean? Well, if we're doing pre-body fat minus post-body fat, and we got a positive number, that means the pre-body fat must have been higher. And we can see that in these means. A mean of 19.79 is higher than a mean of 18.64. So we have strong evidence that there's a significant difference from a 0 difference. It looks positive. In other words, it looks like students had higher levels of pre-body fat than they did post-body fat. How much higher? That's what the confidence interval can tell us. So we check on confidence interval here, and it says we should expect to see a difference in the population. So our parameter, the difference in the population, we feel 95% confident it's somewhere between 0.7 and 1.6. So that difference in body fat, we'd expect to see that difference somewhere around a positive 0.7 to a positive 1.6. And so, you know, if the body fat measurements are around 19 or 18, we're seeing a little bit of a difference there. A 0.7 difference, maybe you notice that, maybe not. But that's the relative, that's the size of difference we'd expect to see amongst the population. All right, so that's how we can do a theory-based approach to analyzing data from paired samples.